Good day, this is Jim Pytel from Columbia Gorge Community College Renewable Energy Technology Program. This is RET 120 Hydraulics. Today we're going to have a discussion about pressure control and we're going to revisit the pressure relief valve. But before we do that, I want to give you guys two incredibly useful schematics that you may or may not see. If you work on a wind turbine, I guarantee you're going to see this guy. This guy is a rotational coupling. Because if you have a hydraulic actuated hub, you're turning the blades from the hub, what is that hub doing? There's not a pressure, there's not a pump, a hydraulic power unit inside each one of those blades. This hub is spinning, and additionally, this nacelle is yawing. So if I had a pressure line and a tank line going into the nacelle, we would expect it to get all twisted up anytime it yawed to face the wind. Additionally, we would expect this one to get especially twisted when we're generating power in the wind. Okay, and by the way, there is not one single big pump down here providing that. There's a booster pump inside the nacelle, and there's accumulators inside the hub. So don't think it's one thing doing everything. So obviously, we don't want these things to twist up. So how we do that is with a rotational coupling. That's the schematic symbol for rotational coupling. Typically, you're going to have obviously one from the tower to the nacelle, and quite obviously, the one from the nacelle to the hub is the most critical one. What it is basically we've got pressurized flow entering here, and via cutout in this light gray thing is rotating, and this dark gray thing is stationary. Okay, so that's rotating. There's a little cutout here, but basically what there is this ring passageway. So all that pressurized flow can in fact leave that A port right there. Same thing with the T. Basically this is stationary. This rotating member here can drain all that. What's this guy right here? Well, it's a case drain, just in case any of this fluid gets past. Additionally, it's providing some lubrication in there. The next pretty important device you're going to see is this guy here. This is a burst disc. Basically, when your pressure relief valve fails, what's your last line of defense? It's this guy right here. The burst disc, appropriately enough, or rupture disc, sometimes called rupture disc, burst disc. Basically, your pressure relief valve, let's say, is set to 2,000 psi, and let's say your hoses are limited to 4,000 psi. Your pressure relief fails, it sticks closed. What happens? Well, your hose bursts once it reaches 4,000 psi. Better idea, let this guy burst at 3,000 psi. So let's say your pressure relief valve fails, the burst disc will fail before the hoses, which is often a great idea. Where is this going to? Well, hopefully it's a reservoir, but chances are it's in a place you don't want it to go to. So again, channelize the, if the burst disc ruptures, channelize that flow to the reservoir or a place that is not going to get extremely dirty. Okay, so two bonus schematics there, rupture disc and our rotational coupling. But the main topic of today's lecture is pressure control. So pressure control, if we change the pressure, we basically are changing the strength of the system. And we've already discussed flow control in quite a great detail. And basically, as we learned, that is controlling the speed of our system. So pressure control is basically we're going to reduce, change, or modify our pressure, and by extension, our force in various branches of our circuit. Okay, there's 6 main types of pressure control valves, and we're going to talk about some of them in great detail. Some of them we're just going to introduce them. But here are the 6 main ones. And these are our 6 main ones. Today, this lecture is just going to talk about the pressure relief valve. But first one, obviously, pressure relief valve. Second one, sequence valve. Third one, pressure reducing valve. Fourth one, counterbalance valve. Fifth one, the unloading valve. And number 6, the brake valve. And the way to kind of organize these things mentally, they are all can be described using the following fashion. It's either NC or NO, so normally closed or normally open in its unenergized state. In unenergized state. So what happens when a normally closed valve is energized? It opens. What happens when a normally open valve is energized? It closes. Dig? Gotta remember that. Okay? For hydraulic fluid, normally closed, it will not flow through. So normally closed, no flow in unenergized state. However, it will flow if energized. Okay? Because it opens. Got it? Schematically, normally closed are typically represented as an inlet and an outlet with an arrow that does not permit passage through. Okay? So our in, out, primary, secondary, P, T, whatever you want to call it, port 1, 2, I don't care. So again, normally closed, the arrow does not connect the inlet to the output. When it is energized, it shifts position and allows fluid flow. Whereas a normally open, this is a normally open valve. And when it's energized, it closes and does not allow fluid flow. Okay? When we get into electrical control of hydraulic systems, this is going to blow your mind. You got to remember this, though. You got to remember this. A normally closed electric switch does allow current flow. So hydraulic, normally closed, electron flow in unenergized state. And when you push this guy, it opens up and current does not flow because it opens. So no current flow when it's energized. You must know the difference between these two. You must know this one. Because as cool as hydraulics are, you are not going to get a job knowing hydraulics. You're going to get a job knowing electronics. So know them both, know electronics. Okay, so that's our discussion about normally closed or normally open. I'm going to clean this all up. So again, that's our first kind of characteristic about all pressure control valves are normally closed or normally open in its unenergized state, and directly related to property A. Basically, they do something, i.e. perform some action when energized. So normally closed, opens, normally open, closes. Dig? Okay, property C. Well, since it's a pressure control valve, it should probably sense pressure. So it's basically sensing pressure. It's got to make a decision off of pressure. Okay, where does it sense pressure from? It could sense pressure from the inlet, it could sense pressure from the outlet, or maybe another place within the hydraulic system. Okay, so some line is coming, it's taking pressure data from somewhere else in the hydraulic system and making a decision off of it. Okay, and property D, basically they're acting via direct or pilot. Okay, so we've already discussed direct acting, and we're going to go back into direct acting versus pilot, or a pilot action. Okay, so these are these are the 6 main pressure control valves, and these are kind of the properties that you can tie in with every single one of these things. And we're going to go about each one of these properties for each one of these valves. And I want to warn you guys, some of these pressure control valves are extremely, extremely very similar. And the property E here that I want you to always keep in the back of your mind, location oftentimes determines function. And especially between the pressure relief valve and sequence valve, you'll understand what I'm talking about. They look the same, and they've got all these same properties here. But sometimes the location determines its function, okay? And you'll see what I mean when we get into the discussion of the pressure relief valve and sequence valve in a little bit here. So again, keep this thing in mind. Location often determines its function in a hydraulic circuit. This right here, I cannot emphasize enough. Location determines function also will help you out when you are learning different schematics. You know, I'm using some pretty standard schematic symbols, but let's say you go to a company that wants to use all sorts of crazy schematics and they just give you a sheet full of symbols that you've never seen before. Figure out a couple things that you do know, and if you get to a valve that's in a certain space where maybe a sequence valve might be, and it seems to be performing the same action, chances are that's a sequence valve. So again, it's just use your what you know about some of these things, and you're going to find out how surprisingly easy it is to identify some of these things. Okay, so let's talk about some of these major properties here in just a little bit more detail. And I'm going to draw a couple very simple diagrams here, and we'll talk about them. So for example, here is the cutaway of a pretty simple valve here. And let's say we want to ask these 4 questions. Is it normally closed, normally open? What's its action? Where does it sense pressure? Is it acting direct or pilot? And we're going to go ahead and I haven't told you the location of it. We're just going to look at this guy. Okay, so pressurized flow is coming in here. Looks like it's blocked and that way. So this is pretty obviously a normally closed valve. Fluid flow from the inlet can't get to the outlet. So if it's normally closed, what does it do? It opens and allows flow. Where is it sensing pressure? Well, it looks like it's sensing pressure from the inlet. Is this acting on a direct action? Yes, because the pressure is directly acting on the spool that opens and permits flow. So it's direct action. So basically what this is just I've redrawn that same direct acting pressure relief valve from way back when, week 1, when I introduced the pressure relief valve. And like I said, we're just going to revisit the pressure relief valve in this video. Okay, so, and we're going to learn some more functions about it. Okay, what else can we talk about in this thing? So E, probably location E, property E, the location. Where is this located? It's probably next to the pump because, again, a pressure relief valve has to be located 6 feet from the pump according to OSHA regs. Property F, which I didn't really discuss earlier, how's it drained? Well, look at what's going on here. Pressurized flow may leak behind here, and if this is a blocked off, that would be bad because then it's an incompressible medium. The spool can't go up, but it's not. There's this drain here. Where is it going? Well, it's going back to the secondary port. That's what's known as an internal drain. And if this thing is internally drained, typically on the schematic, it's not shown. Whereas if it was externally drained, i.e. you have to hook it up to the tank somewhere, that will be shown on the schematic. Okay, so here's our schematic symbol. Here's our box indicating it's a valve. Here's our inlet port. It's normally closed. And when energized, it will open. It's sensing pressure from upstream. We've got this spring, and if I had a thumb wheel right here that I could adjust it, I could make it variable. Okay, so like I said, what if it was externally drained? What that happens is basically there is another passage, another way that I have to send ... to the tank. And if this thing is externally drained, you will see that on the schematic. So why would I ever have an external drain on this one? Well, for this one, it doesn't really matter, especially if it's a pressure relief valve, because this port right here is ideally T, ideally a low pressure port. So if I internally drained it, it wouldn't really matter because that's a low pressure, it's just going to drain away. But what if this, and I know I'm skipping ahead here, was also a pressurized port? That drain internally would have a problem because pressurized fluid would get back there. So that's why you have an external drain. And we'll come back to some valves that are externally drained later on when we discuss the big six here. Okay, so let's go ahead. I'll draw another one and just tell me what this guy is. Okay, so here's our second example. And to me, this guy looks like it is a normally open, because what that's intended to draw there is a land. It's a skinny little land, skinny little valley that fluid can pass through. So that looks like it's a normally open valve. What's it do? Well, it's sensing pressure from this inlet. And when pressure comes to a certain value, for my spring, it's going to close the valve. So basically it's a normally open that will close, that's its action. And we're determining its direct acting because it's acting directly on here. Where is it sensing pressure? It's sensing pressure on the inlet. And then what else can we say about this guy? It's drained. Where was it drained? It is drained externally. So my schematic should technically look like this for this particular one. And it's got a little thumbnail right here. Okay, I didn't tell you where it was too. So it's normally open and in its unenergized state. When it's energized, it closes, does not permit flow. It's direct acting, it's sensing pressure from the inlet, and it's externally drained. Okay, Speaking about external drains, when you route this hose back to the reservoir, do you just stick it in the reservoir and stick it all the way down into the fluid? And the answer is no. Typically, these lines for these drain lines, these external drain lines, always end above fluid level. The reason why is so back pressure conditions don't develop and could potentially change the biasing on that spring. So drain lines terminated above reservoir level. Okay, so again, all pressure control valves have these basic characteristics about them, and we just used two simple valves, a normally closed valve and a normally open valve to illustrate those basic concepts. But now what we're going to do, let's revisit our old buddy, the pressure relief valve, and we're going to discuss this guy in greater detail and how these characteristics affect it. Okay, so what is this guy? Pretty obviously, it's the pressure relief valve. How can we tell it's a pressure relief valve? Well, it's normally closed. It opens when pressure at the inlet exceeds a certain value. Where is it located? Well, pretty obviously, next to the pump. Like I said, OSHA regs 6 feet from the pump and nothing between it and the pump. And we can't really tell if this is direct or pilot action, but pretty much they're all pilots. So let's assume it's pilot activated. And then, is it internal or external drain? Since it's not drawn in there, we're assuming it's an internal drain. And you just go ahead and revisit the lecture on the pressure relief valve regarding the pilot and why it's not drawn on there. Okay, so that's our pressure relief valve. We just revisited the pressure relief valve using these characteristics right here that are common for our pressure control valves. One of the things I want to discuss while we've got this simple diagram located up here. What's this? Center condition. It's a closed center condition. And my question to you, is that the best choice? Well, it depends. What happens when the valve is in the center position? Well, basically, the pressure relief valve is constantly dumping. At what pressure? Well, let's say we set it at 500 psi. There's a 500 psi differential between here and here, while assuming our tank was at 0 psi. Okay, you get what's going on there? Anytime that valve is in the center position, or anytime we're in the straight through position and the cylinder is fully extended, or we're in the cross connect position and the cylinder is fully retracted, we're constantly dumping flow across that pressure relief valve. Is that the most efficient means of doing it? No, because if there is a pressure drop and no work accomplished, the energy's got to go somewhere, so it heats up, or it's noisy. Basically there's a loss of efficiency there. Additionally, who's pumping at 500 psi? This guy. What about this? What if I made a tandem center? I'm still holding my cylinder in a lock. Let's say my application requires that cylinder to be locked. What's happening now? My pump, here's my pressure relief valve. Now there is not a blind path there. My pump can just go to the tank. the pressure relief valve is not activated. And what's the pressure of this thing? Well, incredibly low because it's the pressure of the tank. So what's really neat is you're not constantly activating the pressure relief valve, and you are not warming it up. And your pump is actually acting at a less pressure. It's working against less uh, pressure. Okay, it's just a more efficient means of doing it. So a tandem center. Um, that's not the only way to increase the efficiency of your systems. Let's say you go ahead and you got this. What about a variable displacement pump where we can change the flow rate, and additionally maybe have it pressure compensated where you've got it set up that it basically de-strokes at a certain pressure setting. Basically up to a certain value there, basically it's going to go ahead and stop producing flow. Okay, so there's alternate methods of having circuits become more and more efficient. Okay, so let's again, let's go ahead and revisit our pilot operation. I'm going to go ahead and redraw our pilot operated pressure relief valve real quick. Okay, so here is a pilot operated pressure relief valve, and just for the heck of it, I'm going to go ahead and redo the analysis of here. Basically, pressurized flow is coming in here, and it's acting on this disk of surface area because there's a passageway going through here. The pressure is also acting on that. So pressurized flow at this point right now is acting on the same areas, and basically because of this light biasing spring, the passageway from P to T is closed. Okay, basically equal pressure, equal areas with a little plus on this side, it's holding it closed. Okay, because of this little passageway though, that pressure is acting on a pilot dart. And the pilot dart is this little thing right here that is adjustable via a manually operated thumb wheel. And if you set this spring for a certain value and a pressure exceeds it, it will push back on the pilot dart enough so the P can connect to T via this little passageway here. And basically what happens is basically a pressure loss because this is at an incredibly low pressure. And what happens to our balance here? Again, if this is now suddenly becomes low and this is still high, the whole spool lifts. Allowing a high rate of flow to dump from P to T. And again, how do we do that? Schematically, normally closed, sensing pressure from upstream. Now, this is one of those things where I drew that horrendous box where it's all one device. That is truly the symbol, what you should be using for a pilot operated pressure relief valve. No one does that. Look at how long it took me to do that. Just draw the symbol. People know what you mean because typically they are pilot operated pressure relief valves. Just draw the symbol right here. And just tell me, hey, that's a pilot operated pressure relief valve. It's not a direct. Okay. That is no big stretch of the imagination. It's something that you guys have seen on the first week already. And you're kind of waiting for the punchline here. And here's the punchline. This is what the change is here. I'm going to add some functionality to our pressure relief valve by adding another port here. And this port is commonly known as a V port or a vent port. Or a vent port. And this is that port that we've seen on our labs that we've never hooked up to anything up to this point. And what a V does, it's taking pressure reading from somewhere else. Basically, not only am I sensing from the input, I'm also sensing from my V port. And what is the thing that was keeping this closed, this main spool from opening up P to T? What was the pressure balance between the two? Okay? Because of this internal passageway. So, what would happen if I upset the balance via the V port? And here's a pretty cool application for this. So here's an application here where we've hooked up our V port to this line going to this valve right here. And as long as, spring offset there, as long as it's in this normally closed position here, we're good to go. And let's say this is hooked to the hydraulic system, it's doing whatever, and there's not going to be that imbalance in between our spool that's closing off our passage from, as we said, P to T because of this passageway. Equal pressure on both sides, light biasing spring, forcing it down. Okay, and again, V is hooked up to a normally closed valve. And that hydraulic system can operate and do whatever. But now, let's say this hydraulic system is smashing things up or whatever, and then your buddy Johnny falls into the smasher, and you hit the EMO, the emergency stop button, assuming you like your buddy Johnny and you don't want to see him smashed. You hit that thing, and basically what happens here, it goes to this straight through position. Basically, where's it going to? It's going to the tank, which is an incredibly low pressure. So all of a sudden, this chamber here becomes low pressure tank, and that balance is upset. And what happens? The pressure relief valve opens. Pretty cool, huh? So basically that could be a safety system there. It's a remote operated pressure control valve, pressure relief valve. So that is a remote operation. That's also, sometimes the vent is also called the remote port. Vent or remote port or V port. Okay? So what I've done is I know my pressure relief valve, according to OSHA, has to be 6 feet from my pump. And with nothing connected between it and that. But let's say here at my point of work, I want to be able to control the pressure relief valve. All I do is hook up my vent port, and I can totally disable the system to low pressure. Okay, let's do example 2 here, where we could remotely operate a pressure relief valve. Okay, now I've replaced that little 2-position valve with just another pressure relief valve. So what happens here? And now this pressure relief valve is tiny. And this pressure relief valve, I should draw it correctly, is big. So small and big. And you're going to see the reason why. Let's say I limit my maximum working pressure to 1000 psi. And again, it's super close to my pump and my hydraulic power unit. This guy is small, and it's right next to my point of work. And let's say I need to finally control the pressure for some particular actuator. I don't know what it is. But anyways, I adjust this guy and leave this guy alone. And watch what happens. Okay, let's say I adjust this to 600 psi. That's the appropriate value. Okay, so what happens is at 600 psi, this thing will open because it's normally closed and its action is to open, and it dumps to tank. How much flow is going through there? Well, not much. Basically, it's just the little pressure, the little vent there. What happens here at the main? Well, at 600 psi, that one opened and dumped to tank. What happens here? Again, we were relying on that balance of equal pressure on both sides, but then suddenly this port is hooked to the tank. The pressure balance is lost, and our spool opens up. Where does the main flow go? Right where it's supposed to, through the big pressure relief valve. Pretty cool, huh? So you got a tiny pressure relief valve that doesn't have a lot of flow going through it, controlling a bigger pressure relief valve where all the main flow can go through. So this is, again, close to your point of work. Because again, one thing I do want to stress here is, again, this little passageway here. Because of that little tiny passageway, that is the pressure it's seeing on here. And again, where is it sensing from? It's sensing from there, and that will cause it to open. Okay, so it's not like you got to hook it to someplace else in the system to make the measurement. You just basically make the change on the tiny pressure relief valve. Okay, so which brings us to an important topic directly related to fluid cleanliness. What happens if a piece of particle gets stuck inside that passageway? Well, bad things, obviously. What is the bad thing? Basically, that pressure is going to exceed there because now who knows what's back here? Chances are it's going to exceed it because it might be hooked to the tank. So depending upon that passageway. And it's going to constantly open. So if you get a piece of particle stuck in there, that would be bad because the pressure relief valve would be constantly open. You never develop the required pressure for your system. An even worse possibility with fluid cleanliness, and we'll go into this again too when we talk about fluid cleanliness. What happens if you get particles stuck here and the thing never opens? Aha, even worse problem. Pressure builds and builds and builds till it finds the weak spot, which unfortunately might be right next to your face. Actually, that wouldn't burst there. Probably burst right here. Okay, so fluid cleanliness, absolutely essential to the operation. So what we did is we introduced the concept of pressure control and revisited the pressure relief valve. And what we learned about was remotely operating a pressure relief valve via the vent port. And we're going to go ahead and visit the sequence valve next. The startlingly similar cut